So, hello everyone. Now we'll try to understand this topic on the impact of rigid bodies. Before that, let's just describe what do we mean by impact, and then we'll get into the mechanics of it. Okay. So, largely it means that you have a collision between two bodies which have very large forces involved for a short duration. Okay. So let me put that down in writing. Impulse means collision of two bodies in which large internal forces acting for a short duration rise giving rise to appreciable impulses. Okay, so you already know this. For example, if you use a hammer to strike a pile, okay, so for example in a wood, then that's a impact. Okay, and then obviously there is this impact of vehicles on roads. Okay, so the common part is that you have two bodies which there are large internal forces acting for a short duration and giving rise to appreciable impulses. That's the definition of what an impact is. The two bodies may come in contact, okay, but if the internal forces are not large and if the impulse is not appreciable, then we don't really call it an impact. Okay. Okay. Now, when two bodies come in contact, there are many things happening. Like, for example, there is a sliding or slipping between them that causes some frictional loss. Okay, there may be also loss in the energy due to, say, radiation or sound. You know, when say a glass falls on a piece of glass falls on the ground, there is a noise which also is heard. Okay, so then there is loss of energy due to sound also. Okay, so because of all these losses, frictional and through heat or the sound, we think of impact as a slightly complex phenomena. Okay, and hence to deal with it at our level, we need to slightly idealize some situations. Okay, so that's where we need idealization of impact, because in itself it's a very complex phenomena. Yes, of course. I mean, if the overall motivation is to understand how much of energy has been lost due to sound or light and so on, then we'll have to idealize accordingly. But over here our purpose is to study the mechanics of impact, and it's a big area of research also, for your future, if you find it interesting at some stage in life. So let's see what those idealizations are. Idealization needed. So bodies are modeled as rigid just before and just after impact. and just after impact there is a zero contact time. Okay. Impulsive contact parameter impulsive contact forces and moments. Okay, so we have learned a lot about this until now. And the energy dissipation due to the reasons which we have just discussed is modeled using a simple parameter, is modeled using an empirical, okay, empirical meaning you experimentally find out, empirical parameter called the coefficient of restitution. Now, some things which automatically come out due to these idealizations are that the impulse of all the finite forces will be zero, just because the contact time is zero. Okay, and why do we say finite forces? Because if a finite force is multiplied by a zero contact time, the impulse force will be zero, and that is why in impulse you require these large forces. Okay, if the forces are very large, then the impulses will be appreciable. Okay, so the impulse of all finite forces is zero since the contact time is modeled as zero, and the impulsive forces cause instantaneous change in the velocities of the bodies. Okay, with their configuration remaining the same. So let's try to understand this with a nice diagram. Okay, so okay. This is body 2, this is body 1, this is the line of contact, line of impact. This is ET hat, this is plane of impact. EB is in this direction, ET and EN are already known. Okay, so EB by default will be inside the, as it perpendicular to ET and EN, and then you have this point as A, this point is B. So let me now describe this. So you have two unconstrained rigid bodies. Two unconstrained rigid bodies. Okay, so you have the point A of body 1, you can see that, of mass m1. Okay, so I should write mass m1, this is mass m2. Then this collides with point B of body 2 of mass m2. The common tangent plane at A is called the plane of impact. I have already shown that. Okay, the direction En at A normal to the plane of contact is called the line of impact, okay, shown in this diagram. Now this impact will be called central impact if the centers of mass C1, Ci's of the two bodies lie in the line of impact. So right now I have shown C1 and C2 as over here, okay, but if for example you had this situation, this was the line of contact, okay, and C1 is over here, C2 is over here, this is En, so this is called a central impact. Okay, the center of mass of this, of the two bodies lie in the line of impact, otherwise it's a non-central impact. So let's show non-central impact as well. Yes. C1 and C2, this is En. Remember to always point the direction of En in this impact, okay, so this is a non-central. Even if say one of them is on the line of impact but the other one is not, it is still a non-central impact. Okay, so both of them have to lie in the along the line of impact. Okay, and we have another variation of this called the direct central impact. Let's me call this as a, so perhaps I'm not able to show the contact very well. Okay, this is En hat. Yes, definitely it's a direct impact because C1 and C2 lie along this, and then the velocity V1 and then the velocity V2. Okay, sorry, V1, V2. So this is called a direct central contact impact, sorry. If velocities of C1 and C2 are along line of impact. Okay, just before impact. And if the velocities are not along the line of impact of both C1 and C2, then it would be called a oblique central impact. So you have this. So this goes like this. The velocity of 2 say goes like this. So even though it's a direct impact, because the C1 and C2 lie both along the impact line, the velocities are not along the impact line, and hence it's called a oblique central impact. Okay, so this is how we have defined certain kinds of impact. Now let's try to describe, I mean, let's come back to this particular figure. It's a more general treatment. So what we'll do next is we'll break these, we'll not break, but we'll separately treat these two bodies, body 1 and body 2, and then we'll proceed with the mechanics of it. So let me separately draw them now. So this is body 1. So this is the plane of impact, C1. And then you have this body 2. Okay, this is the same plane of impact, O, and then you have C2, R2. Okay, this is B, this is A, and this is 2. Minus R hat, and then you can write this as R hat. So let O be the point fixed in inertial space, which is coincident with A and B. With A at impact. So if you have, say, omega I and Vi be the angular velocity and velocity of center of mass, Ci, of body I. The I can be either 1 or 2, so just before impact. and just after impact it should be, say, omega I dash and vi dash just after impact to dashed. Okay, now we want to write the velocity of A. Obviously it's VA, so that means the velocity of point A before the impact, just before the impact. So in terms of center of mass, we would be V1 plus omega 1 cross R1. Okay. Similarly, velocity of point B is equal to V2 plus omega 2 cross R2. VA dash V1 dash plus omega 1 dash plus R1. Again, the velocity of B just after impact is V2 dash plus omega 2 dash cross R2. Okay. Now this R hat which you see in this diagram is the impulsive forces during impact. So I'll just write that over here, plus minus R hat are impulsive forces acting during impact. Okay, so let's try to write the equations. So I is equal to delta P and I angular of Ci is equal to delta H Ci. So we have already seen these derivations before, so please check it. Okay, so this is for each body. Okay, so that would have for omega 1 dash omega 2 dash v1 dash v2 dash r hat dash is okay. So we have 5 into 3, 15 unknowns. Okay, because this are 5 vectors and each vector has 3 components, so you have 15 unknowns. And let's see the equations. This is 3 equations. Okay, since it's a vector, this is also 3 equations since it's a vector, and for each body that would mean you have 6 equations for each body. Okay, so let's try to write them. Minus of r hat is equal to, this is for the first body. Okay, I'll write the first, for the first body, minus r is equal to m1 into, what is the change in momentum? That would be m1 v1 dash minus v1. Then for the second body you have m2 v2 dash minus v2. This is 3.58. okay. Next we are trying to write this equation, angular impulse, that would be r1 cross for the first body only, okay, minus r1 hat equal to delta HCI would be written as Ij C1 omega 1j the dash minus omega 1j EI. Okay. Now what we can do is we can first of all, let me give this a number. It is 3.59. Now we can combine this 3.58 and 3.59 by writing it as Ij C1 omega 1j dash minus omega 1j EI hat minus r1 cross. Now this minus of r hat can be taken from here. That would be m1 v1 dash minus v1 is equal to 0. Now similarly we can write for the body 2 the angular impulse. Okay, so we have this already written. Now for the angular impulse r2 cross r hat, I'll just remove this. Okay, and this is equal to Ij C2 omega 2j dash minus omega 2j EI hat .60. Now again we want to combine this 3.60 with this equation, and we can write it as Ij C2 omega 2j dash minus omega 2j EI hat minus R2 cross M2 V2 minus V1 is equal to 0. Okay. So we have a few equations written now. Okay, we require a few more that comes from the friction condition. Okay, so we want to, so you can clearly see that there is a gap between the unknowns, okay, and the equations which are available. So we want to fill out that gap. So this is what, 6 for each body. 6 for each body, 2 bodies are there, and here you have 15. So we have written all these 6 equations now. Okay, and let's not just add some few more equations. So 2 equations are obtained from friction condition. at contact. So if you have, say, smooth contact, if you have smooth contact surfaces of R hat is equal to N En. Okay, this implies that the tangential component of this R hat will be 0. Okay, and clearly this binormal component, okay, which is perpendicular, will also be 0. So there's no vector over here, it's just okay. So the idea is that this impulsive forces will act along the normal, okay, along the normal En. Okay, that's the first case. The second case will be that the rough surface with no slip just before the end of impact. Let's just write that down. Rough surfaces with no slip just before the end of impact. The velocity components of A or B, the velocity component of A and B in the plane of impact are VAT dash is equal to VBT dash, and V dash AB is equal to V dash BB, 3.61. So if you have rough surfaces with no slip, means that they will just move together since there is no relative slip. Okay, and this is just before the end of impact, so you can assume that just after the impact also they will continue to move like this, stuck together essentially. Okay, and the third case, that there is an actual slip. Okay, so the surfaces are rough with the coefficient of kinetic friction mu k, and the slip continues to occur during impact. In the direction of initial slip. So R in this case will be equal to NEN, okay, minus mu k NE. Okay, and E is somewhat of a direction of the component of the relative velocity VBA. So E will be equal to VB minus VA minus, okay, it will be VB minus VA dot En. And this, since it's just direction vector, we must normalize it. VB minus VA minus VB minus VA dot En hat. Okay, the unit vector E is in the direction of component of VBA in plane of impact. This is something which you can easily verify. Okay, that this particular thing is actually the component of velocity VBA in the plane of impact. I think it's quite obvious. Okay. Okay, now we have got some, obviously the unknown is over here. This is the unknown. Okay, in this particular case. Now you had 15 unknowns, okay, and you had 12 equations over here, 6 for each body, so there are 2 bodies, 12 each. So you were short of 3 equations, okay, and from friction you can get 2 more, okay, irrespective of which condition you go for. I mean, on this condition you have these 2 equations, in this particular condition you have these 2 equations, okay, and in the other one also you have these 2 conditions are given. So you have 2 more equations. So now what is the total? 14 equations, okay, sorry, this is a vector. 14 equations, and so I mean you can say that this is a vector, hence it should be 3 conditions, but this n is an unknown, so this makes it only 2 equations, okay. Anyways, 14 equations and what, 15 unknowns, and this is what we have come to now. This situation is called indeterminate. That means just by these equations you cannot solve this problem. So the problem is indeterminate within the rigid body model. As we need one more equation for determinacy. Okay. Now this is where we start seeing the idealizations which we have made in a new light. Now I had already mentioned before that there is no perfectly rigid body, okay, nor are there so-called impulsive forces in this situation, okay. So there are neither rigid bodies nor impulsive forces. The impact analysis using the deformable bodily model is formidable. So let's see what we can do that, okay. So a way out, let me put that. So you should see this as a thought process, okay, that we had 15 equations, we had 12 equations, 15 unknowns, we wrote down those 12 equations, then we added two more conditions due to friction, okay, depending on what situation of friction we were in, okay, and then we were still short of one equation and it seemed like a dead end. Then how to proceed? This is the way to, this is one way to proceed, okay. So we retain the rigid body model and obtain the required fifteenth equation from an empirical relation, empirical that is E is equal to Vs by Va. So this is the velocity of separation and this is the velocity of approach of B from A, okay, along the En. This is just after impact, and V is the velocity of approach of A towards B along En just before the impact. So E, as we have mentioned, is an empirical relation, so E is experimentally determined, meaning once you write this 15th relation you already have the value of E, okay, experimentally determined. This is called the coefficient of restitution. Okay, so V dash Bn minus V dash An is equal to minus E V Bn minus V An. So E is between 0 and 1. So since we want the velocity of separation and approach along En, what do? Well, we just say that is equal to V dash dot En. Okay, this is along the En direction. Similarly, V dash of Bn is equal to VB dash dot En hat. Okay, and VAN is equal to VA dot En hat. Similarly, VBN is equal to VB dot VEN. Okay, so VA and VS are of the same sign. That means that E is always positive. Okay, so you can verify that E is always positive from this. Okay, okay. So if you consider, say, a central impact, okay, we will now show. Let me put out in green anyways. It will be later shown that that for central impact, the change in kinetic energy is proportional to 1 minus E square. Okay, so that automatically means that E has to be between 0 and 1, and this loss of energy, loss of this kinetic energy, gets converted either into sort of sound or thermal and heat and so on. Okay, so this gets converted to sound, thermal, etc. So automatically, if you have, say, E is equal to 1, it is called a perfectly elastic impact. Okay, in this case, clearly delta T would be equal to 0 and Vs will be equal to Va. Actually, this word is not very proper, perfectly elastic impact. We should actually be using called ideal impact, so that we don't confuse between an elastic and a rigid body. So okay, in this case T is conserved. Okay, so ideal impact is also noiseless. Also noiseless, because there is no loss of kinetic energy and there is no chance of you hearing a noise. E equal to 0, the other extreme of it, is called a perfectly plastic impact. Plastic impact. So delta T is maximum and obviously Vs will be equal to 0, since E is the ratio of Vs by A. So if E is 0, Vs is equal to 0. So this value of E actually depends on your material, and actually the combination of the two materials. Okay, so we can just roughly understand how this will depend. So if you have the value, so E is equal to Vs by Va. Va is shown on this axis, and over here you have E, the coefficient of restitution. So as you know, if this value is equal to 1, this is called a perfectly elastic. Okay, now how would E change depending on your material? If you have, say, an impact of glass on glass, it goes like this. If you have, say, steel on steel, okay, and then you may have lead on steel. So as the Va is getting higher, it seems the value of E is somewhat becoming constant. Okay, this is all getting parallel to the x-axis. Okay, so you can make this observation that E tends to 1 as Va tends to 0 for all materials. Okay, but as E decreases, okay, with Va increasing, this is something which you can clearly observe. The reasons of it we don't want to get into right now, okay, but this is something which you can take it for granted as of now. Okay, now if this coefficient, remember this third friction condition, where did it go? Over here. In this particular case, if the coefficient of kinetic friction is not equal to 0, then we definitely assume uh, no slip and solve for R. Okay, with this you can just take this, and if the no slip check, let's do that, let's put that in words. If mu k is not equal to 0, we assume no slip and solve for R. So no slip check is R cross En is smaller than mu s R dot En. Okay, is not satisfied. Then you use 3.62. Okay, so this case is meant for a slip, and if you find out that there is no slip, then you can just easily solve for R. Okay, and if there is a slip, meaning the no slip condition is not satisfied, then you should go for this equation 3.62. okay, Now, as another sort of example, if M2 is much greater than M1. Okay, so this can be like a, say you throwing a pebble on a huge mountain, okay, or say a small meteor striking the Earth or some other planet, okay. So the mass of the second body is much greater than the first body, so we can approximate in this case, we approximate that it's meaning the second body's kinematics does not change, remains unchanged. So omega 2 dash will remain omega 2, v2 dash will remain v2. Okay, so in that case this equation cannot be used, okay, and this equation cannot be used because it's the same value, so you can't at that point use these equations, okay. Don't like use them and say that something is zero. No, you should, this becomes an invalid equation, so you should not be using 3.60 or the second of this 3.58. Okay, let me just now okay, let me now take one case, say C1 VC1 and you have C2 B. So VC2 is say equal to 0. Okay, let's now discuss this. You have something called the impact parameter, that is called B. Impact parameter B. Okay, is the minimum distance between the relative velocity vector vc1 vc2 at c1 from c2. Okay, so this is the minimum distance between the two velocities vc1 and vc2. So in this particular case vc2 is equal to 0, so vc1, let me put that minimum distance between vc1 c2 at c1 from c2. Okay, now this is the first case, I mean, but this is not the most general case. It's just that it is B is easier to visualize in this particular case, that's why I am drawing it like this. In a more general case you can have say something like this, you have C1 VC1, okay, then say you have C2 VC2 VC2, okay, and then so this becomes minus of Vc2. So it has to be minimum distance between Vc1 and Vc2 at C1. Okay, so this is minus Vc2, and Vc1 minus Vc2 will be, say, something like this: Vc1 C2, and say it goes like this. Now this particular distance will be B in this case. Okay, so impact parameter B is the minimum distance between Vc1 Vc2 at C1 from C2. Okay, so this is just some definitions which you have to know, and similarly you can have the difference in the initial and final kinetic energy in a reaction, collision or explosion. Okay, is called Q value of reaction. So reaction can be either collision or explosion, and then you can have this as an either endoergic or exoergic or elastic. This will be when Q is negative, negative Q, positive Q, and 0 Q. Okay, so that just depends on the how much the kinetic energy has either increased or decreased or has remained unchanged. So this is where we can sort of end our general discussion of impact. There are a few special cases to be considered now. So we now discuss the general impact of unconstrained smooth rigid bodies. So you have the figures in front of you. You have smooth rigid bodies, both of them are smooth rigid bodies, and in this case you let, say, Vi equal to Vi t Et hat plus Vin En hat plus Vib Eb hat. Okay, so I mean I equal to 1 will be for the first body, I equal to 2 would be for the second body, and after the impact Vi dash would be equal to V dash I t E t dash plus Vi n dash E n dash plus VIB dash EB dash. Remember at the start of this chapter we had made certain idealizations. Okay, one of them was that the configurations will remain the same, and that means that you can use the same set of basis vectors Et, En and Eb to write the velocities both before and after the impact. Okay, so that was the meaning. Or if you require some other sort of base set of basis vectors, then the configuration would have been changed. So we consider that the configuration remains unchanged, and that's why you can use Et, En, Eb for both before and after. Okay, so V1 and Vi dash, so these are the velocities of Ci just before and just after the impact. Okay, you have this now in the second diagram which you see over here, the bodies 1 and 2 are somewhat drawn separately so that we can treat the forces on them. So you have the impulsive force n hat, okay, so it acts during impact. Actually it is slightly wrong because it's smooth rigid body, so I must draw the n in a certain way. Let's see how. Perhaps something like this, okay, n hat, n hat. This looks more like it. Okay, so the impulsive force is n hat and it acts during the impact, acts during the impact. So let's see, there are 13 equations, 13 unknowns first of all. Omega I dash, Vi dash, okay, and n hat. So this will be 3 components for one body. For 2 bodies it would be 6. This would be 3 components for one body, 6 for both, I equal to 1, I equal to 2, and this is 1. So that makes it 13 unknowns. And we have written 13 equations before. So let's okay, so we can set up 13 equations for 13 unknowns, and we have done this as a general case, so we are studying now special cases. Okay, so one of the things which you should note over here, since the impulsive force acts in the normal direction, so since n hat acts in normal direction, and that means in the E n hat direction, the momentum of each body is conserved in the other directions in ET and EB directions. Okay, so what would this mean? I mean, the mass are definitely unchanged, so we are not mentioning mass, but let's write V1 dash of t and V1 of t. Okay, V1 dash of b into V1 of b, then V2t dash is equal to V dash V2t. Okay, V2b. Okay, so this is 3.64. Now if you see this whole, I mean these two bodies, the impact of the two bodies as one complete system, okay, sorry, say if this is your complete system, okay, there is no external impulse acting on this, and hence the total momentum is conserved. Okay, so let me just rub this out. The external impulse I is equal to 0 on the system of two bodies okay, the total Pn is constant. Pn meaning momentum in the normal direction. Okay, so that was not constant when you were taking the individual values, but if individual bodies as a system, but if you take the whole two bodies as one system, then there is no impulse acting, and hence the momentum in the normal direction should be conserved. So after the impact, m1 v1n dash, okay, plus m2 v2n dash is equal to m1 v1n plus m2 v2n. Okay, we didn't write the masses over here because they would get cancelled on both the sides. However, over here it's not the case. Okay, because m1 and m2 are different. Okay, now the moment of momentum of each body is conserved. Let's see about O. O is this point of contact, okay, point of impact O, which is coincident with this A and B. So HO of each body is conserved so let's write what that would mean. That would mean equation 3.59 and 3.60. I'll show you over here. 3.59, there you go. Okay, so this means that the this value is 0, and hence you can write the conservation of moment of momentum 3.60 and 3.59 each for body 1 and body 2. Okay, so if each body is conserved, so this is something which you should verify. Check whether the H is written about O in 3.59 and 3.60, and if it's not, how do you say this? Okay, and this is the reason that the external impulse, angular impulse on each about fixed point O. Why are we calling this as a fixed point O? Okay, I think you should refer back to the theory which we have just studied. Now you can write 3.59 and 60 using this 3.64. Okay, and you should be able to get IJC1 omega 1 dash J minus omega 1 J EI R1 cross M1 V1 dash N minus V1N EN 0 3.66. C1, sorry, it should be C2 because now we are referring to 3.60. So this was 3.59, this is 3.60. Only thing is we are using this 3.64. Okay, so this is omega 2j dash minus omega 2j Okay, EI hat minus R2 cross M2 V2N dash minus V2N EN 3.67. Okay, so let's see how many equations do we have. It is claimed that 3.64, 3.65, 3.66 and 3.67 are 11 equations. Let's see. 3.64 is 1, 2, 3, 4, 4 equations. Okay. 3.65 is one equation. Okay. 3.66 is what for? Yes. So you will have a repetition over J, you will have a repetition over I. Okay. That should be 3 equations, and then this should be 3 equations. So any vector equation in general is normally 3 equations. Okay. So that's where we have 11 equations. Okay. But remember we required 13 equations. Okay. So let's make up the other two. So the 12th equation is coming from E, the coefficient of restitution. So that will be V dash Bn minus V dash An. So this is what separation minus approach, Vbn minus Van. This is 3.68. Okay, so that's the 12th equation. And how do you find the, let's apply n. So n hat can be m1 change in momentum. So what we do is we apply this impulse momentum equation on this first body to find n. Okay, so m1 v1 dash n minus v1 n. Okay, so this is 3.69. Okay, so it seems we have made up solved the so-called problem. Now we have, so we had 12th equation, this is the 13th equation, and that sort of ends our problem. We can sort of specialize further in this case itself if body 2 is massive. So let me draw the diagram first. Something like this. Okay, it's a massive body, and again we have this A, B, C1, R1, C2, R2, V1, V2, omega 1, omega 2. This will be along En, and you have this tangential Et, Eb. Okay. Let me separately draw body 1 again. you have body 1, this is body 1, and say this is O, A, N hat, C1, R1. Okay, so in this same situation which we have discussed, the 13th equation, 13 equations, if the body 2 is massive, okay, then we know what we do. The kinematically it does not change, so omega 2 dash remains omega, so omega 2 remains omega 2 dash, v2 dash remains as v2, okay, and then vb of n for body 2, b is a point on body 2, remember, so this should be a dash, normal component is vbn, okay. So this automatically means that 3.67 is not applied, okay, because this will not really give you any information, so this is an invalid equation, and similarly this particular equation is not allowed, okay. So this equations are not applied, it is wrong to apply these equations in this case. So I'll write that in red so that you can also again check. Equations 3.65 and 3.67 are not applied. Okay. So the unknown, so you have only 6 unknowns left. Okay. Okay. And omega 1 dash, sorry, omega 2 v1 dash are found. So that can be done from which equations? Let me put that in. Can be found from some of the above equations. I mean the ones which are not applied, okay. So which are those equations? Let's see. We have this one, okay, we have this one, and then we have this one. Okay, and finally you have this one. Okay, so these are the 6 equations. So this is, as you know, 3 equations. This, as you know, is 1 equation, and these 2 are 1 each. So total 6 equations are there. So I mean, I just want to write them here together. So v1 of t, v dash 1 of t is equal to v1 of t, v dash 1b is equal to v1b, vbn minus v dash an is equal to minus of e vbn minus van.
Okay, Ij C1 into omega 1j dash minus omega 1j, sorry, not ij, 1j 1j ei hat minus r1 cross m1 v1n dash minus v1n en hat is equal to 0. Okay, now again, as a sort of further special case of this special case, is that if body 2 which is massive and at rest, then this equation, this one, okay, this reduces to VAN. Okay, so this is just this will change just one of these 6 equations. Okay, now let's take up the second special case, which is impact of unconstrained rigid bodies in plane motion. Okay, so let's take up this one. Let me first draw the figure as always. So this O is fixed in an inertial frame. This is A, this is C2, omega 1, omega 2. Okay, let me now show. So since it's a plane motion, so we have everything in the t and the n plane only. So if this is your En, okay, this will be Et. So let me just show the velocity of 1, the center of mass of body 1, in 2 components. One is v1 of t and the other is v1 of n. Okay, similarly C2 would have v2 of n and v2 of t. Okay, okay, so let's have the impact of 2 unconstrained rigid bodies, okay, with the C1 and C2, and you have a coplanar with the line of impact, and let the axis EB normal to this XY plane be a principal axis of inertia. So EB, let EB normal to this xy plane, so I'm not drawing perhaps xy, normal to this xy plane be a principal axis of inertia. At C for body I. Okay, so I mean EB will be sort of coming over here outside the screen, and similarly for C2 it will be over here. So I mean the idea is that the bodies were moving in the plane before impact and continue to move in the plane after the impact. Okay, that's where the plane motion is coming in. So let's try to analyze this. I mean the claim which we are making over here is this: the bodies continue in plane motion after impact. Okay, so let's see if we can prove this. And provided they were moving in the xy plane before and the normal is along like this. Okay, fine. So let E1 equal to EB is equal to k hat, and E2 E3 be the principal axis at C1, and omega 1 will be equal to omega 1 E1. Okay, and omega 1 dash will be equal to omega 1 dash E1 plus omega 2 dash E2 plus omega 3 dash E3. Okay, fine. So we will be able to prove the statement in green if we somehow show that this big omega 2 dash and big omega 3 dash is equal to 0. Okay, so that's where we are moving towards, but we have assumed it to be true like this for now. Okay, we can't like start with what we have to prove, but eventually that would be okay. Okay, now let's take this R, the impulsive force, as along the normal direction and along the tangential direction. And R1 dash has only ET En components. Okay, since initially they are in the plane xy plane. Now let's write the angular impulse for this C1. That would be equal to R1 cross minus R hat. Okay, angular C1 okay, I11 C1 omega 1 dash minus omega 1 E1 hat plus I22 C1 omega 2 dash minus, it should be omega 2 but omega 2 is 0, that's why we are writing like this, plus I33 C1 omega 3 dash minus omega 3 but that is 0. Okay, now since this is equal to this, hence the individual components of E1, E2 and E3 should be equal to 0. So this implies that omega 2 dash is equal to omega 3 dash is equal to 0, since I22 C1 and I33 C1 cannot be 0. So the only possibility is that omega 2 dash and omega 3 dash is equal to 0. This also implies that omega 1 dash is equal to omega 1 dash E1, okay, hat. Since we had written this as this plus this plus this, but now the other two terms are 0, so this is shown, or this is equal to omega 1 dash k1 hat. This implies a plane motion. So we have already shown that it remains plane after the impact. So the 8 unknowns which you have over here, remember the most general case we had what, 15 unknowns. So since we are discussing only special cases, so the number of unknowns will always be less over here than that. So what are the 8 unknowns? Omega 1 dash k hat, omega 2 dash k hat, v dash 1 n e n hat plus v dash 1 t e t hat plus v dash 2 n e n hat, sorry, this one, okay, and then v dash 2 n e n plus v dash 2 t e t, and r is equal to r dash n e n plus t e t. So 1 unknown, 2 unknown, 3 unknown, 4 unknown, 5 unknown, 6 unknown, 7 unknown, 8 unknown. Okay, so 8 unknowns are there. So let's see what are the equations. This is the impulse momentum equation, and show z is equal to 0. Okay, so this is the, sorry, this is not a vector. So the moment of momentum is a vector, but we are only taking the component in the z direction or this k direction, and that is equal to 0. So this is a planar motion, so this will actually have only 2 equations, okay, and this is only 1, so this is 3 equations, but for each body 1 and 2, for each body 1 and 2, so you have 6 equations which you can write. Okay, now what is the 7th equation? That's about E, the coefficient of restitution, and the eighth equation is about friction. Okay, since see this is not a smooth contact, impact of unconstrained rigid bodies in plane motion, and hence we have taken this R as having both components in the normal and the tangential direction. So depending on the condition of friction, either of them, okay, so there were three conditions. One was smooth, well that is out of the picture over here, and if it is, then you have one equation from there. The second condition which we had read was there were no slip just before the end of impact, okay, and in the last case you have the kinetic friction, which means the no slip condition was not satisfied and hence there was slip. So either way you will have a equation from the friction condition at the contact. Similarly, if you have the body 2 is massive, then what we assume over there is that omega 2 dash is the same as omega 2 v. Now I am not writing this as a vector since we have shown that it only has one component, okay, so that's why I am not writing it as a vector. V dash 2n will be equal to v dash, sorry, v2n, and v dash 2t is equal to v2t. Okay, so you have this, and that automatically means that there are some equations which you have to not include, okay, so don't include impulse momentum equation and HOZ for body 2. Now in this particular special case, if you take one more special case in which you have smooth rigid bodies, okay, so until now we didn't assume smooth rigid bodies, we just had rigid bodies in plane motion. So if you take a special of special, let me put that special of special case, case of smooth rigid bodies in plane motion, so this particular case will be, let me just draw this diagram. Okay, so you have case so in this case you should have, and perhaps I did not show it separately over here, but for say body 1, this is body 1, we had C1 R1 A, and then I did not show this, but it would be that would have a normal component R hat N and a tangential component RT. Okay, so for smooth, let me draw the big diagram again, and then I'll show it for two separate bodies as well. So let's say C1, C2, R1, v1n, and then this will have v1t. Okay, this is en and et, so accordingly, so here again you will have v2n and v2t. This distance is b2, this distance is b1, you have t, you have e, a and b. Okay, and then this rotates by omega 1, this rotates by omega 2. Since it's planar, hence I'm not showing with a vector sign. 1, 2. Okay, and it's the xy plane, I mean nothing to. Okay, so this is the plane of impact, and en is the line of impact. Okay, now in this case you have the smooth rigid bodies in motion, so plane motion to be specific. So you have unknowns. There are 7 unknowns. Let's try to list them. V dash 1n, V dash 1t, V dash 2t, V dash 2n. Okay, then you have omega 1 dash, omega 2 dash, and n hat. Okay. So let me just show the n hat over here in this diagram. This is again, I'm drawing this separately. Okay, so n would be acting exactly along the en direction because it's a smooth, these are smooth bodies, and you have this as t, c1, m1, v1, n. This is momentum m1, v1, t. This is a, o, omega 1. Similarly, this is 2, omega 2. This is e, c2, r2. This would be m2, v2n, and this would be m2, v2t. Okay, so I think we are now better equipped to write the impulse momentum equation. Anyways, this n hat is the impulsive force that we have shown in the diagram separately. So we'll just write equation 3.64 and 65 again. We have already done that, I think. Okay, so we want to write this 3.64 and 3.65 equations. Out of these, some of them are not really needed, so let's do that. Okay, so v1 dash t equal to v1t. The reason is that the momentum in the tangential direction for body 1 is conserved, since the only impulsive force acts in the normal direction. Similarly, v dash 2t is equal to v2t for the body in the tangential direction. Okay, and then we have m1 v1 n dash plus m2 v2 dash n equal to m1 v1 n plus m2 v2 n. This is 3.71. This is the conservation of the total momentum, like for the whole system, since there is no force in the normal direction for the whole system. That's why you can write this. Okay, so this is 3.71. Now the next is we want to write the conservation of moment of momentum. For each of bodies 1 and 2. Okay, so for this one we'll just utilize this particular diagram. Let's see, IZZC1 of omega 1 dash plus M1 V1 N dash V1 N dash R1 is equal to IZZC1 omega 1 plus M1 V1 N R1 3.72. And then for the body 2 we would write IZZC2 omega 2 dash plus M2 V2N dash R2 is equal to IZZC2 omega 2 plus M2 V2N R2. This is 3.73. So one comment about this direction, so the sign of R1 is that if you will have a positive sign, whether the moment M1 moment of M1 V1 N or M2 V2 N about O is in the positive direction, positive K direction, or the negative K direction. So that's so we are not writing this as a cross product, hence you should know this, how this has come about. Okay. Now the velocity of the points A and D, okay, in the normal direction En have the same En component, okay, since it's a rigid body, okay. So the component of the velocity of point A and point D along the normal direction is the same, okay, and the same would be for velocity of this B and point E. Sorry. So let's write that VAN is equal to VDN, and this can be written as V1N minus omega 1 R1. Similarly, VBN is equal to VEN, and this can be written as V2N minus omega 2 R2. Okay. Okay. Now the last term which we want to write is the coefficient of restitution. So we write the separation V dash 2N minus omega so we want to write the velocities of the point sort of A and B in terms of D and E separately, okay. So we want to write the velocity for point this B, okay. So in terms of E, that can be written as V dash minus omega 2 dash R2, okay, minus V dash 1N minus omega 1 dash R1 is equal to minus E V2N minus omega 2 R2 V1N minus omega 1 R1 3.74. Okay, this would, let's see, we have 7 equations, so let's see how we can, which of these can we use equations to solve for omega 1 dash, omega 2 dash, v dash 1 n, v dash 2 n. Okay, let's look out for these ones. So this one, okay, this one, this one, and this one. So you have 4 equations, okay, which are used to find these 4 unknowns. For finding n hat, that has a separate equation. This impulse momentum can be written in the normal. So this is for body 2. Okay, so that solves this particular problem. Okay, fine. Again, I mean, if body 2 is massive, okay, I'm not drawing a diagram because we have done this separate times, but this is what we always do. Omega 2 dash is equal to omega 2, v2 dash is equal to v2, v dash bn is equal to v bn. Okay, so this time some equations are not applied. Let me put it in. Okay, not applied equations. I'll put with a star sign. Okay, you won't apply this one and you won't apply this one. 3.72 is okay since body 1 is not massive, it's body 2 which is massive. Okay, so then you have 3 unknowns, which is omega 1 dash, v1n dash, and v1t dash. Okay, so they can be found out using, let me show those 3 equations. This one, okay, and this one, and this one. So 3 equations, 3 unknowns. I'll also write them separately. 3 equations, v dash 1t equal to v dash 1t, sorry, v1t. Now you have izz c1 omega 1 dash minus m1 v1 n dash r1 is equal to izz c1 omega 1 minus m1 v1 n r1 3.75. V2n minus omega 2 R2 minus V1 sorry V1n dash plus omega 1 dash R1 minus E V2n minus omega 2 R2 minus V1n plus omega 1 R1. Okay, and lastly n hat is again found using for body 1. Okay, if massive body 2 is at rest, massive, then this equation 3.76, it will reduce to v dash 1n plus omega 1 dash r1 dash, sorry, not r1 dash, there's no r1 dash, is equal to minus of e. So v2, all the components are 0, so you will have just v1 n plus omega 1 r1. Okay, now we can take up one more case of central impact of unconstrained smooth rigid bodies. Okay. Okay, so we'll now try to understand the impact mechanics of a central impact of smooth rigid bodies. So if you look at this diagram, it shows central impact by the definitions which we have just learned. And if you do not recall what a central impact is, now is the time to please pause the video and then go back and check. Okay, so for this central impact, we write omega I dash is equal to omega I. Okay, and the reason this would hold true is because the impulsive forces will be passing through Ci, so they would not have any moment associated with it. Okay, so the impulsive normal because it's a smooth, okay, smooth bodies, forces pass through C1 and C2. Okay, now in this case Vi dash can be found out because we have already done this case. Okay, in a more general case, let me check where. The first case itself we had done this, so we can write say v1 2 and v1 dash and v2 dash, and using this 3.64, okay, 3.65, okay, and 3.68. So v1 dash and v2 dash can be obtained like that. So let me just write down those equations, because the first case was a more general case. Okay, there it was not central impact, hence it was more general. So vi dash are obtained using equation 3.64, 3.65 and 3.68. So let me write those equations. V dash 1t, V1t, again there was no impulsive force in the normal direction, there was no impulsive force in the binormal direction. Okay, and V2t dash is equal to V2t, and then we have, okay, so no impulsive forces in the tangential or in the binormal direction for both of them. Then in the normal direction for the whole system there is no force. So if you see the two rigid bodies as a whole system, there is no uh, force, impulsive force. Okay, so this is the conservation of momentum in the normal direction, the total conservation, and finally we have the restitution. Okay, now the velocity of A and velocity of A in the normal direction is the same as velocity of C1 in the normal direction, which is the center of mass, and that is equal to 1 V1n. Similarly, the velocity of B, and in this case in direct impact, okay, if it's not a direct impact, then there is a rotational component because the center of masses will then not be lying along the impact line. Okay, Vc2 V2n. Okay, fine. So we have written, since let's just write. Okay, so we have written all the three expressions of 3.64, 3.765 and 3.68 using this. Okay, now for impact of two unconstrained bodies, rigid or not, the velocity of center of mass C of the system. So when you say velocity of center of mass of the system, it's the overall system remains constant, okay, since the overall momentum cannot change, since external impulse is 0. Okay. So what we want to do is we'll try to write all the governing equations in an inertial frame which is translating with respect to the ground. Okay. So governing equation, just because they will turn out to be easier. Governing equations to be written with respect to inertial frame IC translating with respect to the ground. C is a fixed point. Fixed point. Okay, so if you want to separately, let me just write out terms over here. Sorry, it should be C1, C2, V2n star, V2t star, V1t star, V1n star. Okay, t hat. And then say C is this fixed point. Okay, fine. So all the velocities, so the star means that it's the velocity relative to the IC frame. Okay, and some of them are easy. After the impact and before the impact, this would be same. Similarly, after the impact and before the impact, the tangential component of the velocity of body 2 would also be remain the same before and after the impact. Okay, then we want to conserve the overall momentum for the whole system, which is consisting of the two bodies. Then we would write m1 v1 n star dash, this is after the impact, plus m2 v2 n star dash. Okay, and this is m1 v1 n star plus m2 v2 n star. Okay, this is written as 0. Try to think of a reason why. Okay, what does the star mean and what should be the velocities? Okay, now we write the coefficient of restitution. The separation would be what? Ntn dash minus v star dash 1n equal to minus e v2n star minus v1n star. Okay, now this implies that v1n star is equal to minus e v star 1n, and v2n star dash is equal to minus of E v2n star. Okay, so we'll just break this down into two separate parts. Okay, so that is done. Fine. So we can utilize these properties into over here. Okay. Fine. Now how do we write the impulse? Like always, this is equal to m2 v2 n star dash minus v2n star equal to minus 1 plus e m2 v2n star. Okay, over here perhaps I should separately write that 1n is greater than 0, v star 2n is smaller than 0, okay, in the IC frame, and clearly v1t star v2t star is smaller than equal to 0. Okay, now the impulse is given. Yes, what we have done is we have just used this in this term. Okay, so we can write this expression further as minus of 1 plus e m2 v2n star is written as v2n minus m1 v1n plus m2 v2n divided by m1 plus m2. Now the way this is written, this v2n star is written as this, is the following. I mean, we have, say, the velocity component in IC frame. This is equal to the velocity component in ground frame, okay, minus the velocity component of center of mass. Okay, this is the velocity of the center of mass in the normal direction. So that's how we are able to write this. Now let me just m2, and then this should be m1 v2n plus m2 v2n minus m1 v1n minus m2 v2n, and this divided by m1 plus m2. Does something get cancelled? Yeah, this one. Okay, and m1 can be taken as a common. That's also one good thing. This is 1 plus e, right? Yes, it's a minus of 1 plus e. So I write minus of 1 plus e m1 m2 v2n minus v1n divided by m1 plus m2. Or I can just write the minus sign, or before I forget what this was, I mean, this was n hat. Okay, this is n hat. So 1 plus e m1 m2 v1n minus v2n divided by m1 plus m2. Okay, F average now if I want to write this impulsive force in terms of the average force acting during this time delta t, so we have it as F average is equal to n hat by delta t, or 1 plus E m1 VA by delta t, okay, and m2 is going down, so it would be 1 plus m1 by m2. Okay, fine. So from this we can conclude that the average force, okay, for an actual impact during the duration delta t, so the average force is directly proportional to, so VA is this velocity of approach. Okay, I should write it more clearly. Okay, so this is a velocity of approach, and it is this equal to the square bracket v1n minus v2n. So this is proportional to VA, okay, and F average is inversely proportional to delta t, okay. As E increases, the coefficient of restitution, F average also increases, okay, and for a given m1, okay, for a given m1, if m1 by if for a given m1, if m2 increases, then m1 by m2 decreases. 1 plus m1 by m2 will also be decreasing, and this implies that F average will be increasing, okay, since 1 plus m1 by m2 is in the denominator. And when m1 by m2 tends to 0, this means that F average will tend to 1 plus E m1 m1 VA by delta t. Okay, so if m2 by m1 increases, the F average increases, and if it increases a lot, then m1 by m2 will tend to 0, and so it increases and it becomes like this. So okay, so this value is 1 plus E into m1 VA by delta t. Okay, so this is how the average force varies. So if we want to write, for example, delta t, in this case, the change in the kinetic energy is the kinetic energy after the impact and kinetic energy before the impact. Now the kinetic energy is half into m1 v1n square star square minus v1n star square, okay, plus half into m2 v2n star dash square minus star 2n square. This is equal to half into, okay, v1. Okay, so let's see how we can write. We have, okay, this can be written as half into e square minus 1 into m1 v1n star square plus m2 v2n star square. Okay, so this are all little stars. Okay, so this is something which you should, I think, verify. I'll put that down in red. You have the expressions in terms of the coefficient of restitution just above over here. Okay, so I think you should be able to use many of them. Okay, so I think this is the expression which you should be using. Okay, so do verify it, don't leave it. Now once this is done, I want to write this as half into e square minus 1. Let's take v1n star is common, so let me just take that v1n star square as common. Then I can write it as m1 plus m2 into v2n star square by v1n star square. Okay, now I want to write this as half into e square minus 1 and where did it go? You can use this expression. Okay, let me put that in another ink. This is equal to 0, so you can write v2n star by v1n star square is equal to m1 square by m2 square. Okay, this thing can be written over here. So we want to now substitute this. So this would be m1 plus m2 into m1 square by m2 square, and the rest remains. So this will remain v1n star v1n star whole square. Now again we want to write this, let me just write this as common, m1 plus m2, 1 plus m2, m1 by m2. Now this v1n star we want to write again in terms of the center of mass. So we'll write first in the ground frame minus now the velocity in the center of the center of mass, v1n plus m2 into v2n m1 plus m2 and the whole squared. Okay, this means that we can write half into m1 m2 by m1 plus m2 e square minus 1 v1n whole square, sorry, v1n minus v2n whole square. Okay, fine. So I mean, the reason we are doing this is because this change in kinetic energy will only happen because of the change in the En, along the En direction. So this is only because change in En component of VCIC. Okay, so this is equal to VIN star. And we have already written what VIN star is. Okay, this one. Okay, so if you have this delta t, so this is all delta t smaller than equal to 0, this implies, because this is a positive number, this is a positive number, this is a square, so it cannot be negative. So the only possibility is that e square minus 1 will be smaller than equal to 0, and this would mean that the coefficient of restitution is 1. Okay, this is something we had told, sort of you were told before but not shown. Okay, but now you have shown this. If the change in kinetic energy after the impact, sorry, the change of kinetic energy during the impact is negative, then E is between 0 and 1. Again, if this second body is massive, okay, if body 2 is massive, then V2 dash is equal to V2 and the conservation of momentum cannot be applied along the normal direction now. Okay, so that would mean that you only have V dash 1t is equal to V1t, V dash 1b is equal to V1b, V dash 2t is equal to V2t, V dash 2b is equal to V2b. And V dash 2n is equal to V2n. Okay, and V2n minus V dash 1n is equal to minus E V2n minus V1n. Okay, so this is just this case. Where did it go? These equations 3.77. Okay, so this has been modified for the case when M2 is massive. Again, as a last case, if this massive body is fixed, that case clearly v2 dash will be equal to v2 will be equal to 0, and then this 3.78, this will reduce to v dash 1t is equal to v1t, v dash 1b is equal to v1b, and v2t dash is equal to v dash 2n is equal to v dash 2b. This is all 0. Okay, just because the entire velocity component is 0, so all components are 0, and v dash 1n will be equal to minus e v1n. So this is 3.79. So with this you can also, with this one you can also say that the velocity component of the light body 1 along En is reversed and reduced by a factor of E. Over here you have reasons why this kinetic, the change in kinetic energy is negative. Okay, so think about it. Okay, fine. So if you let me just draw the diagram first. So one body is massive, and then this is the light one. Sorry, so this is let me just draw this. Tangential direction, normal direction. So if you have, say, this as your v1 direction, okay, so the tangential component of it is v1t, so I should write, I think, in a separate color, and this is the velocity after impact v1 dash. So let this angle be theta I and this be theta r. Okay, so let me now break them down into tangential components first. So this is the v1 of t, and this is v1 dash t. Okay, the tangential component before and after the impact. Then let me draw the normal component, that is v1n with this arrow, and this one is what, v1n dash. Okay, so we have shown all the sort of velocities in this case, components of velocity in this case. Now if you choose for this, I mean, we are continuing with the same discussion of a massive body. Okay, now if we choose massive body which is fixed, okay, this is shown as fixed, this is body 2. So choose ET in the plane of En and V1. Okay, so this theta r is the angle of reflection, and theta I is the angle of incidence. So we say that tan of theta r is equal to V1t dash by V1n dash. Okay, now V1t dash is actually, according to this one, it is equal to V1 of t, and V1n dash, sorry, V1n dash is equal to E. So because there's a modulus sign, that's why we are not taking the minus sign. This is V1n. Okay, and this is called tan of theta I divided by E. So since E is between 0 and 1, this quantity will always be greater than tan of theta I. This implies theta I is smaller than equal to theta r, and both of them are clearly smaller than pi by 2. So if theta r is equal to theta I, okay, this means that there is a elastic impact, and if this theta r is equal to pi by 2, then it means it's a plastic impact, or so called perfectly plastic. You should know the coefficient of restitution in that particular case. Okay, so if you draw this again, sorry, should be, so this is your, say, V1, theta I, V1 dash E is equal to 1, V1 dash, and then the last V1 dash. So this is E is equal to 0, this is theta I, this is theta r is equal to theta I. Okay, in this case that is for elastic, and if it's plastic then V1 dash will be like this. So theta r will be 90 degrees, this is plastic, and somewhere in between you have this situation. Okay, so this is diagrammatically shown, and this is again body 2, so no guesses over there. This is body 1, this is body 1. Okay, body 2 is massive and is fixed. Okay, so if you have, say, a You can also find the efficiency of this exact situation, okay, in which you have this body 2 which is fixed, and body 1 which is sort of moving towards it and impacting. So let's do that. So you have this direct central impact of two unconstrained smooth rigid bodies without rotation. So if you have this is 2 at rest, okay, this is 1 C1 C2, this point is B, this is A, and then this goes by this velocity v1n. Clearly this is the normal direction, okay. So you should see a video of a drop hammer. You will be able to visualize this. So please pause the video, open an internet browser and look up for a video of drop hammer, okay. This is a situation in which you have this 2 as your fixed body and 1 as your striking body, okay. So in this case you want to finally get v-1n and v-2n, okay. What you will do is you will be writing this momentum after the impact, okay, and this is m1 before the impact, v2n dash minus v1n dash is equal to minus e 0 minus v1n. v1n dash, okay. With this one, v1n dash will be equal to 1 minus e m2 by m1, 1 plus m2 by m1 v1n, okay. You can just use this one and put v2n dash from over here, okay, and v2n dash similarly will be 1 plus e by 1 plus m2 by m1 v1n. This is 1. Now the efficiency or the fractional decrease or whatever we would want to call is the original kinetic energy minus the final kinetic energy with respect to the original kinetic energy. So this would be 1 minus e square of 1 plus m1 by 2. Okay. So this decrease, the fractional, this decrease will be large if E is small, okay, and the decrease, this fractional decrease will be large if m1 by m2 is small, because if m1 by m2 is small, 1 plus m1 by m2 will be small, and overall it's in the denominator, so eta will increase. So this is also some sort of a loss, fractional loss of kinetic energy. Okay, this finds use in a so-called forging operation. Perhaps you may have learnt or heard about it, and a drop hammer is an example which helps you do that. Okay. Again, I mean, if M1 is very small compared to M2, then by equation 1 you can say that V1n dash is equal to minus E V1n, and V2n dash is equal to 0, and eta is equal to 1 minus E square. Okay, so for 1 and 2 we can write it like this: if M1 is very small compared to M2. Okay, now if the other case is there, like M1 is much greater than M2, then V1n dash is equal to V1n. Okay, and V2n dash is equal to 1 plus E V1n, and eta will be tending to 0, or almost be equal to 0. Okay, there is no loss of kinetic energy, so it's better to take a very small striker over there. Okay, this is also used to say in hammer or pile driver. So please check up the videos of all these things, hammer and nail. Okay, you apply, the hammer is much heavier than the nail, and that's the one example. And similarly you have a pile driver which is used in uh, uh, civil engineering applications. Okay, so if you look at this second equation, this one, you want E to be large and M2 by M1 should be small. Okay, so to impart a large velocity to the pile in a pile driver, okay, you want this to be very large, and this will be large if E is large and M2 by M1 is small. So that's one other remark which you can have. Okay, and lastly let's take up sort of one more case, I think 4 other cases. Okay, so if you have, say, body 1, this is body 2, C1, R1, A, comma O, 1, 2. Okay, let me just separately draw them now. This is C1, this is R1, okay, this is A, comma O, this point, and say this is the impulsive reaction force, this is body 1. So if body 1 impacts a perfectly rough surface. Fixed surface, or maybe I should call a fixed body too. Then obviously VA dash is equal to 0. Omega 1 dash is found, you have to use the conservation of HO of body 1. So I omega j about O omega 1 j dash EI hat is equal to IJC omega 1 j EI hat minus R1 cross M1 V1. Okay. This is the reason for this is that just after the impact, this O becomes a point of the rigid body. Okay, since just after impact, VA dash is equal to VO is equal to 0. That is O becomes point of rigid body. One. Okay, so if you have, for example, two unconstrained rigid bodies which stick together as a single rigid body after impact, okay, these are two situations where you can think of how you can solve this problem. I think you have all the tools, so I'll just put down as in red two unconstrained rigid bodies which stick together as a single rigid body after impact. Okay, so you can think about how you would solve this problem, though it's, I think, everything practically which we require has been done over here. Okay, so some more special cases, I mean, you should not constrain yourself to these four cases which we have learnt. Okay, these are just tools which help you sort of polish your understanding of impact mechanics, but in reality you should be prepared for any situation, and the first general treatment which we have done is the key to all this. Okay, so hello everyone. Before we study about the steady precession of a gyroscope, there is a small task which you should do. You should know what is a gyroscope, okay, and what are its applications. Okay, so what you have to do is you should open your any search engine and look up videos of what is a gyroscope, and perhaps you will be able to understand exactly how this works, and then you should learn about its application in many of the devices and machines which we use nowadays. Okay, so it has wide scale applications. So this is a task for you. Please pause the video and come back only once you have done these two things on your own. Okay, now let's define a gyroscope. A gyroscope is a rigid body with two equal principal moments of inertia R11 is equal to I22 at its material point O which is either the center of mass C, or let me just write this, a fixed point in I. Okay, so this is a definition of a gyroscope. It's a rigid body with two equal principal moments of inertia. I11 is equal to I22 about a point O. The point O can be a material point. Okay, it can be either the center of mass or some fixed point in I, which is an inertial frame. Okay. Now, if you have by this time learnt about gyroscopes, you know the way it behaves is not exactly how it is in our intuition. Okay, so it somewhat contradicts our intuition of how a gyroscope should behave. So that is something which you should have figured out by now by looking at lots of fascinating videos about this. Okay, so let's now have one, say, a gyroscope drawn. Okay, and let me just draw a different color. Okay, this is E3 hat, and this is point O. So this is a disk. Okay, I should have drawn this more correctly. This is a disk. Okay, and okay, so you have a gyroscope spinning at high angular velocity. What is the value? It is S E3 hat. Okay, so E3 direction is shown in your figure. Now, uh, if you apply an instantaneous angular impulse to it, then the moment of momentum will be changing, and that will happen according to this. Okay, now, which means that, I mean, if you had this, sorry, if this vector was your HO and this is the HO plus delta HO, then I angular O is equal to delta HO. This vector is delta HO. Okay. This angle, let's call this as theta. So the angle theta what is the angle theta? It is between this vector h plus delta h and HO for a given HO for a given delta HO, sorry. This only depends on HO. Okay, and it will be, if HO is large, then theta will be small. Then theta is small. Okay. I mean, one easy way is to just draw it with a diagram, and perhaps you should be able to visualize this. Okay. For a given delta H naught, draw a vector H naught of say this length, and draw a vector then H naught of the other length, and the delta H naught must be the same. Then you will observe this statement. So this you can draw and verify. Okay. Okay. Now HO is equal to I33O SE3 hat. Okay, because this value is equal to omega. Obviously this has a higher magnitude for larger S. Okay, so since this is true, has a higher magnitude for a larger S, this implies the high angular impulse will cause a small change in direction of HO. That means it's a theta is small. See, over here you have seen that if H naught is written like this, okay, basically I omega in the 3 direction, and we should only have the principal components. So this has a higher magnitude for larger S. That is true. If S will increase, HO will increase. And here you have learned this, that if the HO is large, then theta is small. Okay. This implies that this angle theta will be small if HO is large, and HO is large because this gyroscope is spinning at a high angular velocity. Okay, this magnitude is high, and that is why we say this angular impulse will cause only a small change in the direction of HO. So this theta will be really small. Okay. This also implies that the change in direction of omega is also small. Okay, since HO is directly proportional to the omega. Okay, or there is only a little change in the axis of rotation. Okay, so we get this spin imparts stability to a gyroscope. So let's consider three specific motions. Specific motions of gyroscopes. We'll do it one by one. Let me draw. And then you have this as a rotation P, and this is a capital E, this is small e3, this point is O, this rotates by S, so this direction is E2, this is E1. The first motion which we are discussing, the gyroscope is spinning at a constant rate. Okay, constant rate SE3 hat about the body fixed axis E3, okay, through O, with E3 itself precessing at constant rate P capital E about an orthogonal axis E. I hope you can visualize what's happening. Okay, fixed in I. Now let's write the moment which is required to maintain this motion. Okay, that, I mean, it's the moment due to a couple. So this is the moment due to couple required to maintain this motion. This has a very good word, it's called gyroscopic couple. Okay, so we have this frame formed by, we are mentioning a triad. One is E3, the other is E2, which is equal to E. Okay, sorry, and the next is E1. Okay, so this rotates with respect to I at rate omega is equal to P E2. Okay, or capital E, whatever else. Okay, so let's apply the second axiom over this. Let's first write omega is equal to P E2, sorry, P E2 S, so plus S E3. Or it is just to say that this SE3, the spinning rate of the this body, is actually relative, okay, to that of the bigger frame which is rotating at P. Okay, so this is just the relative angular velocity. Now write the moment about O, moment of momentum about O, I11 O P E2 hat plus I33 O S E3 hat C naught. So this should be PE2 across I33 OSE3 hat. Okay, this implies that C naught is equal to PS. Okay, then E2 cross E3 is E1, so you would have I33O E1 hat, or this can be written as P cross I33 O S. Okay, either of them are okay. So P over here automatically implies PE, and S has been written as SE3. So you can see that the C is normal to both E2, which is the precession direction, and E3, which is the spin direction. Okay, let's take up now the second sort of second motion, second specific motion. Let me draw that over here. I mean, I'm drawing these rotating parts as with a circular cross section, but it does not mean that it will be like that. Okay, the only requirement is that the I11 must be the same as I22. So let's put this as the precession axis. Okay. And then you have something like this. So this would be P E hat. Then you have this as your E3. This has S, and this angle is theta. Okay. This is E1 hat. Now in this specific motion, the axis of precession, or the precession axis E is at an angle theta to the spin axis. Again, we want to choose E1, E2, E3. Okay, so choose EI. Okay, the triad like in the previous case, such that E1 is in the plane of E and E3. We have shown E1 in the diagram. Okay, so E1 is in the same plane as that of E and E3. Okay, okay, so we want to write the angular velocity of this frame, omega, the capital Omega, as a sort of PE, and big E is written in terms of the small e as sine theta E1 hat, okay, plus cos theta E3 hat, plus, okay, that's it. So this is the frame which has E1, E2 and E3 rotating by this value. Let's now again use the Euler's axiom. First write the relative angular velocity as PE plus SE3. This is equal to P sine theta E1 hat plus cos theta E3 hat plus SE3 hat. Okay, so this and this is okay, and P is written, capital this PE is written from over here. Okay, Fine. Now write HO is equal to I11O P sine theta E1 hat plus I33 O S plus P cos theta E3 hat. Now MO will be written as what? H dot OI. I, because I mean you are using the Euler's axiom, that's why the inertial frame. And this is omega cross HO. Okay. Now omega is this, HO is this. One can take a cross product of them and write this as I11O P square sine theta cos theta minus I33 of O S plus P cos theta P sine theta, then E2 hat. Okay, I11 P square sine theta cos theta minus I33O S plus P cos theta P sine theta. Okay, E2. So this is equation 3.81, and the earlier one, I think maybe I didn't give it a number. Yes, this is 3.80. Okay, so this was the third sort of second specific motion, and let's now take a body which is a gyroscope essentially. So we have I mean in these two cases we didn't require this to be a okay. So let's see I11, let's see the difference of this third case. We are making this as a requirement over here, okay, and this is a gyroscope by the definition which we have made. So this is rotating about a fixed axis. About a fixed point O. So let me now draw that. Some sort of a this is E P R O E1 hat. This we want to be called as E3 hat. This is rotating by S. Okay, this has a center of mass, weight will be mg, and this is h. Okay, from O, this angle is theta, and this is a solid line which tells us that this is a part of this. Okay, so let's try to find the minimum value. Let's write it over here. Find the minimum value of S so that the precession constant theta is possible. So for that we can just use this equation 3.81. Okay, so MO will be equal to minus mgh sine theta into E2 and then like just put this MO in this 3.81. Okay, so let's see, that would give us I11O minus I33O cos theta p square minus I33O SP plus mgh sine theta is equal to 0. Okay, now this implies that theta is either 0 or pi, or the square bracket is 0, meaning I33O cos theta p square minus I33O SP plus mgh is equal to 0. This is equation 1, and from this, since this is a quadratic in P, okay, you can find the two roots of this P1 and P2, that is equal to I33O S 2 times of I11O minus I33O cos theta. You should know how to solve a quadratic equation, so that's why I'm not going into that detail, but you should please check what I am writing is correct. Cos theta GH cos theta 1 by 2. This is equation 2. So you have these two precession rates, okay, and obviously the determinant has to be positive for real roots. S square is greater than 4 I11O minus I33O mgh cos theta I33O square. So this will be true if S square is greater than 4 I11O minus I33O mgh by I33O. Okay, cos theta will be not a problem. Okay, now if you what to do, so if you have S as large, which is large in a gyroscope, okay, so it's because we assume that the angle rotation axis doesn't really change much. Okay, if for large S, okay, you can write this equation using the binomial expansion. Okay, so this 1 plus minus this power of 1 by this particular term, essentially you can use binomial theorem. So you should all know binomial theorem by now. If not, please pause the video and check this. Okay, so this gives you P, which is approximately equal to I330 S divided by I11O minus I33O. Let me just write this. I11O minus I33O cos theta. Similarly, P2 would give us mgh by I33OS. So this is the fast precession rate, and this is a slow precession rate. So all this is very relevant to, say, a spinning top which you have. So if in a spinning top you have this initial precession is at a constant theta, then there is a wobbling motion, okay, and then that is due to omega 3 decreases due to friction, okay, and when that happens, at some point this condition 3.82 gets violated, and hence the precision at constant theta is not possible. Remember, we started off with precision being at a constant theta. Okay, so you can observe all that in a spinning top. All these things. Okay, we have some sort of minor remarks to make. So let's call them as remarks. Okay, so this equation 1 over here, this can be written in terms of omega 3 by replacing s term. Okay, this s over here can be replaced, so we can write equation 1 in terms of omega 3. Okay, just replace s by omega 3 minus p cos theta. So you can check this particular diagram. Okay, you can so p cos theta, so s my omega 3 will be equal to s plus p cos theta, and that's why you can do that. I think we must have also written it also somewhere. Okay, so you can just transform it accordingly. Okay, so eventually, I mean, this will give you I11O cos theta p square minus I33O omega 3p plus mgh is equal to 0. Now again quadratic, so p1 and p2 would be equal to I33O omega 3 by 2I 1 O cos theta 1 plus minus 1 minus 4 I 11 O mgh cos theta by I 33 O omega 3 all square 1 by 2. mgh cos theta by I 33 O square. So the determinant has to be constant, sorry, positive. Okay, so that is 3.83. It's just the same equation as one, only it is written in terms of omega 3. That's all. Okay. And just like the previous case, it is satisfied if omega 3 square is greater than equal to 4 mg h I 11 O divided by I 33 O square. Okay. So from 3.83, from this equation, you can say that if you have theta of t at all times, this is equal to 0. The motion will exist if omega square is greater than 4 mgh I 11 O by I 33 O. Okay, this is called a sleeping top. Remember what the angle theta is. Okay, in all this, let's not forget. Okay, this is the angle theta. If this angle is 0, okay, we are speaking about that situation. Now for this particular case, you can expand the the square root term, okay, using the binomial expansion. So that would give you I 33 O omega 3 by I 11 O cos theta. P2 is equal to mgh by I 33 O omega 3. Okay, this is equation 6. Now if the center of mass is below this point O, okay, in that case for C below O, theta will be greater than pi by 2, and then cos theta will be smaller than 0. Okay, in this particular situation 3.83 will hold and stable precession exists for all values of omega 3. Okay. The reason would be, I mean, then this entire thing would become a negative number. Okay. And this will be a positive number since it's a square. So a positive number will always be greater than a negative number. Okay. Okay. Now the second comment which we have over here, if P is a small or theta is almost equal to pi by 2, then equation 4 implies omega 3 is equal to mgh by I33O P plus I11O P cos theta by I33O almost equal to mgh by I33O P almost equal to S. Okay, since omega 3 has a relation with S, okay, and this is almost equal to S because theta is 90 degree almost, so cos theta would be 0. So C naught, I mean, if you check, sorry, in this situation, when this theta, when this becomes almost equal to 90 degree, okay, then you would have a gyroscopic couple C naught that will be equal to mgh. Okay, you can assume that, right, because this couple will be mgh sine theta, right, and when theta is almost 90 degree, this will become like, so I mean, you will have something like this, okay, and everything is like this. C will be over here, mg will be acting, h is this direction, okay, and this s is equal to omega 3, okay. Okay, so C naught in this case is mgh, and equation 4 is what? Equation 4 over here will give you a relation between I33 and mgh, because this cos theta will become 0. Okay, so equation 4 gives I33 O is equal to I33 is omega 3p is equal to mgh. Okay, now if mo is equal to 0, then clearly mgh is equal to 0 in equation 1. Let's check that. Okay, mgh is equal to 0 because mo is equal to mgh sine theta, and that equation 1 will give us p is equal to 0 or I33OS I11O minus I33O cos theta. Okay. Lastly, if there is no spin, s is equal to 0 for a given p, and then the equation 1 would just become, let's see, equation 1 would just become cos theta. Okay, sure. And then this is the term. Okay, so this would imply that cos theta is equal to mgh divided by p square I330 minus I11. Okay. Lastly, we can just briefly discuss the general motion of a gyroscope. Okay. So because it's a general motion, we will not have a well-defined geometry. Okay, so let's have something like this. Let me draw the axis first. Y, X, and then this is Z, this is point O. Okay, let me use another ink now, which is E1, E2 and E3. So this is E1, E2 and then E3. Okay, so the angle between this and this is theta. Between E2 and E3 is 90 degree. Between E1 and X is phi. Okay, and this particular angle between Z and E2, this is pi by 2 minus theta. Okay, and let's show me also, this is also n, this is rotating by theta dot psi dot. Okay, so you have a gyroscope with O being its center of mass or a fixed point with principal moments of inertia. So I11 of O is I22 of O. Okay, now the orientation of E3, if you see, is described in terms of theta and phi. Theta is the angle between E3 and K or Z. Okay, and phi is the angle between the normal, which is n or E1 direction, to the plane of E3. Okay, so the plane of E3 forms angle phi between the with the E1, okay, or the n direction. So K and the x axis, so this plane is formed by, let's say, let me write it, phi is the angle between E3, sorry, between n E1 to the plane formed by E3 K and x axis. Okay. E2 is coplanar with E3 and K. So phi dot is the spin rate about A3. Okay. Only E3 is attached to body. So omega is again the frame E1 or EI, right? E1, E2 and E3 frame. So omega is the angular velocity of that frame. Small omega is the angular velocity of the body. So let's write this down. This is phi dot k hat plus theta dot E1 hat. We have written this before, okay? This is actually slightly more specialized form of it. So we had written this in the more general form earlier. Please recall where. Okay, plus phi dot sine theta E2 plus phi dot cos theta E3. Again, the angular velocity of the body, small omega, is big omega plus phi dot E3. This is just the relative angular velocity. Then you can write theta dot E1 plus phi dot sine theta E2 plus phi dot plus phi dot cos theta E3. HO, the moment of momentum about O, will be I11O theta dot E1 hat plus phi dot sine theta E2 hat plus I33O phi dot plus theta dot, sorry, psi dot plus phi dot cos theta E3 hat. So if you want to write the equations of motion, okay, they would be F equal to mac, and the moment about O is by the Euler's axiom. Okay, this can be written as O for EI frame plus omega cross HO. Remember, very first class we have, or one of the first classes we have learned about any vector being written like this. Okay, so I mean, if you can break it down into two parts or three parts, since MO is a vector, so it will have three parts. The first component will be I11. I mean, you do this cross product with everything which you have. You have omega, you have H naught. Okay, so I11 about O theta double dot minus phi dot square sine theta cos theta plus I33 over phi dot sine theta phi dot plus psi dot plus phi dot cos theta, and MO2 is equal to I11O phi double dot sine theta plus 2 phi dot theta dot cos theta minus I33 O theta dot phi dot plus cos theta. And this will be d by dt of psi dot plus phi dot cos theta. So this I can leave out as an exercise for you to verify. Okay, all you have to do is just do this part. Okay, shouldn't be a problem at all. So this ends our discussion about the general motion of a gyroscope. Okay.